Okay, so I'm going to share the screen. Yeah, let's see. Interesting. It doesn't give me a figure. All right, well, let's see what we got. Let me click on the thing here. I can work with that. All right.
And
Um,
the problem for me is that like Green's theorem in the textbook says the boundary of the area, um, the boundary of the area shows you um, the integral because all of the internal arrows cancel out, and you're just left with the arrows on the boundary. And then this question
right,
says remove the boundary from point D to A.
right.
So now we have an area without a boundary, and it looks like
Yes.
1D. So I just thought, oh, my first answer is going to be 0 because it's just a line. Um, but that's not the case. So I don't get what's going on.
Well, yeah, let me copy it down real quick. Okay. So we've got this kind of trapezoidal figure, but it's actually not a closed figure. So I'm going to go to my overhead here. All right, so in its current form, if you worked out the line integral of this path, you'd have to actually work out three separate line integrals because this is not a closed path. So what we're going to do is we're going to kind of cheat. We're going to do step one, we're going to close the path, or we're going to close the loop. So we're going to add in a boundary from D to A. Okay, so we're actually going to add in this boundary over on the left. And then what we're going to do is we're going to work out the line integral for that guy. And so we got to parameterize that boundary. So it's basically it's well, it's going to be 0 to in t for t. Well, actually, I take that back. It'll be 0 and 9 minus t for t between 0 and 9. And the reason I want 9 minus t is I want the path to start at 0, 9. So the x is staying 0 no matter what. When t is 0, we're at 9. And when t is 9, we're at 0. Does that make sense why I put that 9 minus t in there? Let me know. So that's our parameterization. And this is I always found this a little bit to be a little awkward. I'm going to rewrite it slightly different here. The vector field is sine x plus 4y, comma 4x plus y. And for Green's theorem, what you do is, well, okay, first, no, I take that back. We need to do two things. We need to close the loop, add the boundary from D to A, and work out the actual line integral along that path. So the line integral for just this path is, well, here's our R. Our
Yeah, I got
R,
the Green's theorem part for the closed area.
sure. Our R prime is 0, negative 1. And then the vector field, well, X is 0, so the X parts just drop out. Y is 9 minus T, so I'll make the substitutions. I'm substituting y equals 9 minus t into y, so I get 4 times 9 minus t, which is 36, take away 4t, and then I get 9 minus t for here. And then I'm going to dot f and dr. R prime is dr, it's the same thing. So the 0 just dots, gets rid of that guy, and I have negative, so it just becomes t minus 9. Okay. And that becomes my integral. My integral is t minus 9 dt, and the bounds are 0 to 9. And I just work it out. So this becomes what, 1/2 t squared plus, yeah, take away 9t from 9 to 0. So I get 81 halves, take away 81, and 0 drops out. So I'm going to get negative 81 halves. All right, so that takes care of just the path. I'm not sorry, just this path right here. So this is negative 81 over 2. Okay. Now we can use Green's theorem on the entire loop. And that's the beauty. So rather than working out these separate line integrals, uh, we're going to work out Green's theorem on the interior, and then we'll subtract off whatever this guy was, which was negative 81 over 2, and that'll give us the rest of the loop. So the second step is to do Green's theorem on the interior. That's going to be a double integral. Um, so our formula is, if this is m and this is n, Green's is always n sub x minus m sub y, yay. N sub x is 4. M sub y, it looks like 4. All right, I'm not going to complain. So I get 0. All right, well, that's nice. I kind of wasn't expecting that, but looks like we get 0 as the overall um, Green's theorem. So 0 would indicate the entire, all the way around the loop. That's the line integral. Well, if this guy is negative 81 over 2, then all 4 of these have to add up to 0. So the rest of the path, its line integral is going to be 81 over 2, positive 81 over 2, because all the paths must add to 0, or the line integrals along all the paths must add to 0 in this case. Okay. If I got a different number here, let's say I got 6, then you just have to make sure they add up to 6. So it's real simple arithmetic. Does that make sense?
Yeah, I think I mean, I got the Green's theorem part, so I just have to do a line integral for the subtract the boundary.
Yeah, it's kind of a you can't, yeah, technically we're cheating, but it's a way to work out a whole bunch of other line integrals by closing off. If they don't form a loop, go ahead and form a loop, and then just work out that line integral and then subtract it from the Green's theorem.
Yeah, and mine is not 0, but that's okay. All right, thanks.
Yeah, I think I got lucky because I wasn't expecting that. All right. So that was a question on Green's theorem. That was number 5. I'll make a note of that. 13.4. Um, any other questions on this one? All righty. Anybody want to go next?
I have a question on one of them.
Yeah, go ahead.
On section 13.6, I think just in general, I'm having a difficult time understanding this section, like what specifically to parameterize and when to do it. So I guess just like a specific question I could use help with is number 7 on
Yeah, let's,
13.6.
let's take a look at number 7. Um, yeah, hold on. I'm going to copy it and I'll share it. Find the surface area of the part of the cone. So 13.6, number 7. The sphere is just the standard sphere radius 7, centered at the origin. And then we've got above the cone, what do we got here? Z equals x squared, square root x squared plus y squared. And if I draw it, um, I don't know if I can make a good drawing. So this, you're gonna get a cone that comes like this. So you're gonna get like kind of like a little portion thereof. All right, you know what? We're gonna just beat this one with a stick. This one, um, all right. So when you're doing straight up surface area, it's basically just well, technically, it's you parameterize the surface area and you take the double integral of the magnitude of the parameterization. Okay. However, most times, if the surface is already defined, what's the word I'm looking for? Explicitly, so where z is isolated, we can actually get away with just using this formula because you end up just getting this massive um, you get this formula because you're taking the magnitude of the cross product. You don't have to go through this whole rigmarole most of the time. In the case where you have the sphere itself, what we're going to do is we're going to solve for z, and you're going to get square root 49, take away x squared, take away y squared. Okay. And so if I do z sub x, I get 1 over 2 of that whole thing. Then I have to work out its chain rule is going to be negative 2x. Z sub y is going to be, well, okay, it'll just be similar, negative 2y and all this. Let me get this all written down first, and then I'll kind of summarize. You can do a little simplification with the twos. The negatives stay behind. Okay. Um, so then what we're going to do is just work out this darn thing. When you put it into this formula, it looks really nasty, but actually it works out. Let's see. That's the one. Then I have this thing squared. And then this guy squared. Now, what something nice happens here is that the radicals go away, the negatives go away. You actually have x squared plus y squared. So I can bring these together under a common denominator. Now I can even get that one incorporated. I get everything under a common denominator. It's going to look a little messy just for a second. This is the x squared plus y squared over here, plus sign here. The numerator, if I treat this as 49 minus x squared minus y squared, it's going to happen over here too. And something nice happens. Do you see what happens?
Yeah, it all cancels out at the top
Yeah.
for the 49.
Yep. And 49, of course, is a perfect square. So you get 7 over this thing on the bottom. So now it's just a question of integrating that. That's your integrand. Um, and so we come back to the picture here. We just need to figure out where these guys intersect. And the easiest way to do that is just to substitute. So if I substitute the cone into z squared, the square just takes away the radical. And I'll just kind of tuck it in right here. You get x squared plus y squared, and you get another x squared plus y squared because we squared away the radical when we plugged it in for z equals 49. If I have two x squareds and two y squareds, so I have x squared plus y squared, I factor that out, I just divide by 2. And the reason I'm doing that is that this is the region of integration. This is a circle of radius. It's going to be 7 over rad 2. I have to take the square root of that. And the reason I'm doing that is that I've got, even though this thing kind of depressed nicely, it's still a double integral with radicals. But now I hope you're seeing that maybe we can get away with using polar. So let's use polar. Let me just pause here and I'll go over any steps that you're wondering about.
I think so far this makes sense. I think the thing I've been having issues with is starting out what units to parameterize.
Okay. Let me
Like starting out with polar or
tell you what. Let me finish this off, and then I'll go back and I'll discuss general parameterization tricks and techniques. Um,
okay.
because yeah, it doesn't necessarily settle into like a couple neat algorithms. As far as this one's concerned, we're double integrating this function over a circle of radius 7 over rad 2. So we're going to do a polar integral, double integral. Um, I'll take out well, it'll be 49 minus quantity x squared plus y squared. So 49 minus r squared. And remember, I have a 7 on top. I'm going to put an extra r on top because that's the Jacobian. The bounds for r are 0 to 7 over rad 2, and d theta would be 0 to 2 pi. Oops, sorry about that. So that's your double integral converted to polar. It's not a bad double integral. This thing integrates by u to u. And I always mess this up, so I'm just going to do it over here. So it'll be negative 1/2. So if u is 49 minus r squared, then du is um, negative 2r dr. Let's see, put a 2 out there, put a um, should be negative 7/2. And then I should have it should be, so we add 1, so we get plus 1/2. So 49 minus r squared to the 1/2, and divide by that, so we should be multiplying by 2 again. All right, so I'm going to make sure I did that right. So I claim that the answer here should be negative 7 and then radical 49 minus r squared. Let's double check that. If I take the derivative, um, so it's going to be negative 7, and then it's going to be 1 over 2 radical 49 minus r squared. And the derivative of that's negative 2r. Negative, so the negatives cancel, the 2's cancel. Yep, it worked. Yay. So I get a happy face. Okay. Anyway, yeah, because even after all these years, I still sometimes um, I'm not so sure I did that right. So this, actually, I did the integral. My bad, my bad. I did the integral. I'll just go ahead and kind of write it right here. It's negative 7 and then 40 radical 49 minus r squared, and it's the bounds are 7 over rad 2 and 0. And at this point, geez, it's going to get a little messy. It's going to be negative 7 and then 49 over minus 49 halves. So that'll be radical 49 halves. And then minus 7 when I plug in 0, that gives me radical 49, which is 7 again. So this is plus 49. This is going to be negative 49 rad 2. Yuck. You know what? I'm going to leave it. That's just the R part. The theta part is so easy. It's just 2 pi. So um, this is just a big old constant as far as theta is concerned. So I claim that the answer is going to be this lovely expression looking something like that. And I'll admit I kind of did that fast, so I hope I did it right. I'm curious. I'm going to look it up. Um, I get a 49, they get a 98. What did I do? Oh, no, no, I did it right. Yep, I did it right. Yay. All right. Everything's cool. All right. So let's address the question of just general parameterization. Um, So in a surface integral, the whole point of doing surface integrals is that you're setting yourself up to do the flux integrals in the next section. A surface integral, they're nasty, but they're double integrals, and you have some function of f of x, y, z. Then you have some surface, and that has to be parameterized. So you end up getting a whole extra expression here, and they become pretty heavy functions. I'll say this, in like case one, if the function is written explicitly, so that's z, that means z is isolated. Then when you do your z sub x and z sub y, and you go through the trouble of doing the cross product and then you do the magnitude, you're always going to get, you can just skip to the radical. It's going to be 1 plus and then f sub x quantity squared plus f sub y quantity squared all under the radical. That'll always happen. You can just skip right up to it. So that's in the case when it's explicitly um, defined. If it's implicitly defined, well, at that point, you pretty much, um, for example, you have to remember some implicit parameterizations. Do you remember how to? Well, let me figure out what I want to write here. I'll call this case two for implicit cases. Um, oops. Do you remember how to parameterize a sphere?
So this is like having x equal r cosine theta, y sine r sine theta.
It's actually you got to do it in spherical. So even I forget. Geez, it's going to be
Mm.
yeah. It's x equals r. It should be cos theta. I'm trying to picture it in my mind.
Sine phi.
Oh
Sine phi,
yeah.
yes. Y is r cos theta cos phi. Z should be r.
And y is cosine, or y is sine theta sine phi,
That's right. Yeah, and then z is r cos phi.
cosine
Cos phi.
phi.
Yes, thank you. You know, this is parameterized in two variables because r is actually treated as a constant here. You would be parameterizing in theta and phi. This is if you have a sphere. But I'll
Shouldn't
be honest with you, you can do it explicitly just as well, like the one we just did. I mean, it gets heavy with the algebra, but it usually works out.
Because this would have been my first thought was to use this on the last one without
Let's
remembering
take
like
a
the
look.
z first, just because it has to do
Yeah,
with the sphere.
I'm just going to take a look at some of the questions on 13.6 and curious. When I teach this in class, I usually just concentrate on a couple of the main cases because we're so out of time that I can't really I don't have time to do all the cases. Let me see if I can find a good one here.
when it
Um,
comes to skipping to that like radical one plus f sub
yeah,
x squared and all that, is that kind of like replacing the magnitude of r sub u cross product with r sub v?
it is. I just use X and Y.
Or yeah, okay. Okay.
That's exactly what it is. It always
So
happens
if you
that
have
way.
that, you can substitute it with that. Okay.
Yeah. So let me give you, I'll just make up a couple cases. How about a cylinder? Suppose I had a cylinder that was uh, parallel to the z-axis. So the z-axis is coming through the middle, and it was up here at z equals 4 and down here at the origin. And let's just say it was base was radius 3. So it was a circle of radius 3 extended 4 units into the z direction. So this would be a case where you could parameterize it in two variables. The x and the y could be traded out for cosine and sine. Oops. I'll just use theta for now. And the z would actually be an independent variable, independent of the theta. I will just use z the way it is, from 0 to 4. So now so the parameterization, if you really want to try to follow what the normal usage of letters are, I admit it gets a little nuts. What if I just let u be the theta and v be the z? So I have 3 cos u, 3 sine u, and then I have just v. Okay, but I have to have the bounds. So u would be between 0 and 2 pi, and z would be, I'm sorry, v would be between 0 and 4. So that would be the parameterization of this cylinder, and these would be the bounds. These will eventually become your integral bounds. And then you can go through the r sub u, r sub v calculation to get your normal vector. And then you have to take the magnitude of that. And another one I saw in your homework was a cone. In fact, I'm going to bring it up. It's the last one. It's number 12. Give me a moment here. Consider the cone below. Let's come up with some parameterizations. The height of the cone is 2 and the base is 9. Let's see if we can parameterize this darn thing. So it's only got so 9, 9, and 2. Okay. So I'll stop the share. I'm just going to jump in head first. The X and the Y's are circles. I'm going to leave some space in front. I'll just do traditional cos theta and sine theta. But notice that Z, well, if I put Z down here, if I just let Z roam between 0 and 2, I need to come up with, let me do that again. If Z roams between 0 and 2, I need to come up with a couple of expressions here that, so such that when Z is 0, I have a radius of 9, and when Z is 2, I have a radius of 0. So for example, looks like I just need a linear change. So I want to make sure that when I plug in 0, I get 9. And then when I plug in 2, I get 0. So that would be, I'm just going to I'll just see what I'm 2. 9 halves Z should do the trick. Let's make sure that makes sense. If I plug in 0, these guys are gone, and I have a radius of 9, so I'm down here. And when I plug in 2, the 2's cancel, 9 minus 9 is 0, so this seems to work. So if I use my traditional U and V lettering, Z would be the V, and theta would be the U. That would be the parameterization, and then you definitely need the bounds. So U would be between 0 and 2 pi. V would be between 0 and 2. Those become your integral bounds. That's how you parameterize a cone, for example. Um, I don't know. I don't think I can cover all the possible cases. These are kind of the common ones. Does that help whoever asked this question originally?
It does help, yeah. I think just a mixture of all the different kinds of coordinates mixed in with all of the different parameters is starting to make it somewhat confusing, but that does help
Yeah,
out. Thank you.
surface integrals are a lot. And usually you end up with a radical, which just makes the actual integration very difficult. So you have to do the whole parameterization process just to get your R's, just so you can do R sub U, R sub V, and cross them. And then you have to do the magnitude. So yeah, these tend to take a while. Um, and oftentimes they get really messy. It's not if you've gotten to 13.7, a flux integral is a form of a surface integral, but you're also, I hope you're seeing the divergence theorem, which can be used to handle cases where you have a closed solid.
I definitely have some questions about that.
Yeah, me. Yeah, go ahead.
Oh, let me look at my notes. I just didn't see the divergence theorem in the lecture, and maybe I don't see it.
Let me go to it sometimes it barely gets covered if at all. I'm going to show you some stuff you can look at.
Yeah,
Um, so the very last thing we do is 13.7, which is surface integrals and flux. And let me scroll down the questions here. Um, I think like number 4, I'm just looking at it real quick.
that is one that I got stuck on.
Yeah, I'm just, there's 8 questions. Actually, only looks like number 7 also. Well, but that one would be tricky. I think number 7, you can just do it traditionally. Um, which one are you asking about? Number 4?
For to be honest, so seven I did good, or I did
Yeah.
fine. It was six that tripped me up the most, but I think that was just the amount of time I spent on it. And then five was actually the one that got me.
Okay. Um, compute the flux of the vector field. What do we got? Y plus 3 minus xz. Yeah, give me a second here. I'm pondering it myself.
Hmm.
Okay. Um, it's F dot NDS. All right. All right. All right. You know what? Actually, now that I see it, let me share it. Um, compute the flux of the vector field. Um, Let me copy it. It's 5y1 and negative 5xz. And the surface is y equals x squared plus z squared, such that x squared plus z squared is a circle less than 4. Okay, that's fine. That just helps us with the bounds. Oops. And we're oriented in the positive y direction. All right, so this is a case where, all right, so in general, a flux integral is this guy. Okay, I'm going to stop the share here. Sorry about that. It's F dot NDS. Okay. Um,
And then F is uh f of r f of another function, right? F of,
Right.
I'm gonna say RUV, but I know we're not gonna use RUV. I think it's R XZ here.
Yeah, so it's a little awkward because we have it explicit in terms of y, so it's going to be um, when I do its partial derivatives, I'm going to have y sub x, which is 2x, and y sub z, which is 2z. Now, here's the deal. You choose your n vector to be, now since we're doing it explicitly in terms of y, there's two possible n vectors, and I'll explain this in a second. One of them will be, uh, I'll say y sub x, y sub z, and -1, or the other one will be negative of that, and then +1. That's kind of your generic n vector. And the reason that that works out that way is you may recall that we're trying to get a unit vector. It's actually going to be this guy divided by its magnitude. But then ds is actually the magnitude again, so the magnitudes cancel out. I'm going to go to my web page actually. Give me a moment here. I'll share it with you in a second, but I got to find it. All right, so it's yeah. All right, you know what? I'm going to share something with you real quick. It's on my web page. So this is my notes for setting up a flux integral. The general form is this. It's the double integral f dot nds. But here's where it gets interesting. You do the parameterization, and then you do your n vectors, and you have two choices here. And um, it's always going to be one of these two choices. And we almost always choose the one that has positive. So, for example, in this case, z is isolated. So we have z is -1 or 1. In the case that we're going to do it with y isolated. And but you don't need to go through the trouble of writing the radical parts down here. These are supposed to be unit vectors. But then ds is this guy here. Well, these guys, when you put them together, they just cancel. The radicals cancel. And so you get this big old expression here. Looks nasty, but the radicals cancel. And so you're just left with a dot product, really, of the vector field dotted with the, I guess you could say the uh, the n without the unit part, but it's still good enough. So in this particular case, I want this one right here because we were told that it's oriented in the positive y direction. And so then all we need to do here is just fix the original vector field to get it in terms of x and z. And so I don't want let's see, I want to get rid of that y. Well, y is x squared plus z squared. The other terms look good. The n is what we see here. It's actually negative of 2x, 1, and negative of 2z. Now, I'm going to make a mention. This one right here seems to just be a lucky accident. Okay. It could have been something else. So then when you do your double integral, I'm sorry, when you do your dot product, you get -10 quantity x squared plus z squared plus 1. And then plus these guys negatives cancel, you get negative, so you get plus 10 xz squared. Okay.
Are you missing an X on the first kind of grouping, the first portion of the dot product from the 2x, minus 2x?
Oh yeah, I am. Oh, sorry. Okay, that'll just simply shove an x right. Let me just rewrite. It'll be a -10x. Yeah. So this thing, let me just spread it out a little bit. Oh, okay, this is nice. We get a little lucky. These guys cancel. So I get negative 10x cubed plus 1, and that's going to be my integrand. So I've got the integrand set up. I just need to figure out what I'm integrating over. It's going to be a dx dz integral. And here's where that information up here, this is a paraboloid that opens in the positive y direction, such that the input variables x and z are within a circle of radius 2. And so, well, if I draw it, I mean, I can just draw it right here. I'll do the x and the z. It's just a circle of radius 2. Um, Now the question is that it would be, for example, z equals square root of 4 minus x squared. The bottom part would be z equals negative 4 root of square root of 4 minus x squared. So my question to you is, we worked this all out, all fine and dandy. We've got this. We're integrating over a circle. What do you think you might want to do?
Polar coordinate.
Yeah, I agree with you. So, um,
Oh, actually, I don't want to do that. If I'm integrating, because I don't have a z in the integrand.
um,
What are my bounds of x? Aren't they
X would
4?
be if okay. Actually, if I it actually doesn't matter. You know what? Let me just rewrite it. It really doesn't matter if I do Z first. If I do Z first, my Z bounds would be the parts of the circle. My X bounds would just be negative 2 to 2. Okay.
Yeah, so z is integrand of z will equal to 0.
Yeah. No, hold on. It won't. No, it won't equal 0.
Oh.
Because okay, when you integrate,
I think you still do dx dz.
it doesn't matter. If I do dx dt, I would just have to simply write these as x equals rad 4 minus z squared. Um,
Yeah, if you do dx dz, then you end with a constant,
I don't think that's the
right?
code. Let me go with this. If I do it this way, this is going to get ugly. I'm going to get radical. I'm going to get a pair of radicals. So my question then is, do you want to use polar on this one? I would probably opt for that. In other words, we've got a circle here, and this is just looking scary. I don't like radicals in bounds. Man, that's rough. So I think what I'm going to do is I'm going to try polar. So polar, the bounds of zero r will be 0 to 2, and theta will be 0 to 2 pi. And all we need to do is just make the adjustment here. X is r cos theta. And so really it's a question of how hard is it to do that. If I do a polar integral, it'll be negative 10, and then r cos theta cubed minus, plus 1. I remember I'll have an extra r from the Jacobian. And so, oops. And so the bounds would be 0 to 2 for r, 0 to 2 pi for theta. Really, it's just a question of, I mean, we can handle r pretty efficiently. Um, let's distribute, we'll pull that in. We'll have 10r, negative 10r cubed. So we actually have negative 10 r to the fourth cos theta plus r. Oh, I think we're going to get a little lucky here. All right, give me a second here. And actually, the cube would be on the theta. So this r got cubed, and then this r came in and made it a fourth power. So I'm integrating with respect to r. So let's say I get negative 10 over 5 r to the 5 plus 1 half r squared. from 2 to 0. And I'll put the cosine back on. I know it's supposed to be there. Um, I get that's -2. I'll just put it on now. It's just going along for the ride. When I plug in 2, I get 32 for 2 to the 5th. Here I get +2, and then 0 just drops out. And so I get -64 cos cubed theta +2. And I'm going to integrate that from 0 to 2 pi d theta. And that should work out pretty good because the cosine cubed can be integrated by borrowing a cosine squared, treating that as 1 minus sine squared, and then suddenly you have u du. I apologize. This gets pretty heavy. You're so close to the finish line. Oops. But this is just the way it is. This will integrate pretty sweet. This becomes -64 sine theta. Oh, I see something really sweet. Yeah, everything's gonna get plugged into sine. And when you plug in 0 and 2 pi into sine, what happens? Let's see.
0 is 0.
Yeah, these all go away because when you're plugging in 0 and 2 pi into the sine theta, into the theta, which is in the sine, you get zeros. And the only thing that survives is this guy. So I get 4 pi. Geez, all that hard work. I'm going to make sure that seemed too easy. No, that's the way it works. All right. Again, I admit that I kind of ran through a lot of these calculations fast. So I don't know. There's a lot of stuff going on here. Does this raise more questions or does it help you?
It helps a little bit. I think that it might just be that I need to study trig identities a little better. Because when I got to the cosine cubed in the homework, I panicked and just went back and worked it out.
Okay.
Or just kind of brute forced it with the other method.
Yeah. And again, there's just no shortcut on these. This, unfortunately, is just how they do. This one worked out. We got lucky here. If this didn't happen, we were in for some heavy duty work.
Mhm.
And then we also got a little lucky toward the end because we ended up integrating a sine. Or I'm sorry, we integrated. Yeah, right here that's a u to u. So yeah, we integrated. Well, we got sines. Let me just say it that way. And when you plug in 0 and 2 pi, they just drop out. So that was nice. You could have probably shortened this using symmetry, but I'm not comfortable doing that. It's pretty tricky to see the symmetry on these guys. I would just gut it out. All
I
right.
had a question,
Yeah.
if you're ready to move on, about kind of adjacent to this. When it comes to like orientation for flux, how do you, I guess, determine which kind of normal vector or, which the normal vector and like the cross product of the r sub x and r sub y, that's the same thing, right? It's just,
Yeah.
so when you're trying to figure out which, kind of, I guess, positive or negative version to use for the correct orientation, I guess I sometimes don't really understand exactly what is the thing. Because if it's like says it's pointing away from the z-axis, well, that's kind of been like, I don't really know exactly
Well,
how to
yeah, it depends on the
go
shape of
about
the
that.
object. Um, Oftentimes it'll just be stated that positive orientation is positive z-axis, for example, so upwards. Um, if it's a closed solid, it's always away from the interior. And for a cylinder, for example, since a cylinder, let's say it wraps around the z-axis, it's always going to be away. So that might be what you see it in the reading. It's going to be away from the interior.
So that would mean that you have, well, so that's kind of what I got in one of these, was that situation. But when you get a normal vector, like I had two of them. One was the x and y component were both negative and the z was zero. And then for the other one, it was obviously inverse, so positive, positive, and then zero.
Okay.
But kind of like thinking about it, it seems like both of those are pointing quote unquote positively, in the positive direction, like away from the z axis. So I didn't really understand how to interpret which one to use, if that makes sense.
Um, it should be clear in the reading because it is otherwise it's vague. For example, if it's a regular z equals f of xy function, we just have to tell you what it is. We say it's either positive z or negative z. If it's a closed object or an object like this, which is kind of closed, like a cylinder, it's almost always pointing away from the interior. A true closed object, so if we somehow close this all off, by definition, the positive orientation would be away from the interior. But for something that's like wrapping around but still has like you can access the interior, normally it's just good form to call the positive orientation away from the z-axis, for example. And that would create the vectors always pointing away, radially, if you will. But usually it should be stated. You don't ever, it's most of the time you don't need to worry about that because at worst, all you'll do is you'll just get a negative of the correct answer. That's it. It'll work no matter what. You'll go through all the 27 steps to get it worked out, and you get 72 over pi. And then maybe the correct answer is negative 72 over pi, something like that. Um, so it should be stated in the question.
Okay. Yeah, it is stated, it says it's oriented away from the z-axis, but both of the normal vectors that I got
Mhm.
made sense in that way. They both seemed like they were, oriented away from the
What was the
z-axis.
shape of the object that you were dealing with?
It's a cylinder. I mean, I can tell you the
Okay, in the
question
case of a
thing.
cylinder, again, I guess if you parameterize this, you just want to make sure. Well, yeah, I would probably just parameterize this using sine and cosine. It should probably just take care of itself, to be honest. Um, yeah, you know what? Can you tell me? Yeah, I'm going to give you the share. You want to do that?
Yeah, I can bring it up real
All
quick.
right. So you should have the ability to share now.
Okay.
Um,
Does that show up?
yeah. So compute the flux of the vector field x, y, z through the curved surface of the cylinder. X squared plus y squared equals 9. Bounded by. Okay, so you know what I think your mistake might be? When you parameterize the cylinder, you have two variables. One of the variables will cover the actual circular part. That will be x equals 3 cos theta, y equals 3 sine theta. The other
Yep.
variable will be z, and z will actually roam between the two planes that you see there. And so you'll have 3 minus x minus y and 6 minus x minus y. Do you see that?
Yep. That's what,
And,
yeah, I did that.
and you'll have to parameterize those. You shouldn't be getting zeros when you parameterize your components. You should have, well, it shouldn't be, you shouldn't be getting zero. So it looks
Oh,
like
yeah.
you need
I,
a third you need two variables, and one of them is going to take care of the circle. That'll be the theta or u. And then the v
yep.
will just be the z. And um, so you should be getting plus or minus.
I didn't get
One.
zeros in the parametric
Okay.
function. I got them after doing the cross product of the partial derivatives with respect to,
Hmm.
whatever. So when I got the normal vector, I had -3 cosine of v, which I used
Okay.
for theta, and then -3 sine of v, and then 0 because I guess
Okay.
it's a
Yeah,
cylinder,
I see that because it'll drop out. Then the other one will be like 0, 0, 1, right? Or something like that.
Oh yeah, yeah, yeah. So that was 0, 0, 1, and then -3 sine v, 3 cosine v, 0, and then when I cross product them, I got -3 cosine v, -3
Okay.
sine v, 0.
You know what? It shouldn't make a difference when you're doing the cross product. Um, it, I'm just doing this mentally, but it shouldn't make a difference. It'll give you a valid n.
Okay.
Um, yeah, I know which one that is too. So yeah, okay. Yeah, so what did you get? Yeah, you get the sine and cosine. It should work. I don't see, I'm just not seeing where it would falter.
Okay.
Yeah, I'm sorry. It seems to me like it'll just,
Okay. So just even using the negative version. So in this scenario, both normal vectors would be valid.
yeah, because
Okay.
when you set up your normal, it, dang it, I'd have to actually work it out myself, but it seems like it would work. Um, okay. Yeah, go with it. I give you permission
Cool.
because
All right.
I'm just not seeing how it won't work, but it should.
Okay.
Yeah.
Cool. All right.
I'm actually looking at their key, and of course, they skip about 12 steps.
Right.
Um, Actually, in this case, some geometry kind of kicks in, so you get a little, again, lucky. I hate to say that, you don't always get lucky on these things, but sometimes the math kind of helps.
Yeah. Like when I got to the actual integrand, it reduced to just 9.
Yes, and then when you
But
plug in your
with
bounds, you get a lot of cancellation, don't you?
right. But when I
Yes.
did it the other way, I think I got -9. But maybe not. Either way,
All right. Well,
positive or negative.
yeah, I'm sorry. I can't give you a more definitive answer on that.
That's okay.
To me, it seems like it should work just fine.
Okay.
I'm not seeing where you're going to falter. All
Good
right.
enough for me.
Hey guys, I'm gonna go ahead and power down here. It's been an hour. I will post this to my website. I'm sorry for the confusion. I don't know what was going on, but it wasn't letting me join the thing like normal. I had to sign in through my ASU and go through all that. So I might do another one on Monday. We'll see. So And but and then unfortunately my schedule is such that because I teach at ASU Tempe, so I'm going to be kind of on the road as well as teaching my classes. So I'll be able to check in sporadically on Tuesday, and then same thing on Wednesday. It's looking like Wednesday late evening or late in the afternoon, early evening is when I'm going to actually get back to tackling our class. So you guys will be done, and then I won't. I'll be able to get all this stuff probably Wednesday and Thursday. I probably won't get grades posted until Friday, so I'll let everybody know. It's gonna be an icky week for me. All right, y'all. Five,
Have
four,
a good
three,
day.
two, one. Thank you again.